Examine this gravity-free path. This picture is from the physics classroom, and he shows this great diagram with this gravity-free path. You could imagine if you were in outer space and you threw a ball, it would move at constant speed because acceleration on the x is equal to 0, right? Once it leaves the cannon, there's no force acting along this path, so it's just going to keep moving the same way it was moving to start with. Right? So this will be constant speed because it's moving to the right and it's no acceleration. For the vertical motion, now if we look at this, right, what we're looking at is we're moving down and acceleration is down, right? And acceleration is down because net force on the y is down. Therefore, it's increasing speed. And if you look at this, it looks exactly the same as an object in free fall. So how do we end up, when we look at a projectile, how do we end up with a curved motion? Why is that? And the whole point here is that we have to combine these two. When you take one vector that goes this way, we'll call it the x, and we take the other vector that goes this way, well then, when you connect these, the resultant, what you actually see is motion this way. We call that the resultant. This velocity here is just this piece, and that's changing every moment, right? That combination, as Vy gets bigger, right? If we leave Vx about the same and we make Vy bigger, look what happens to the direction of the resultant. The resultant now tips down even more because the y component has a bigger emphasis. So that's why you get this changing angle, right? And as that happens moment by moment, you end up with a curve, right? You connect enough line segments together, you get a curve. The thing to remember is that the x component and the y component, both of them, are independent of each other. So they do what they do, right? On what the x does the x, the y does what it does on the y, but they act simultaneously. And what we see is the resultant. Which changes minute by minute, moment by moment. And that's one thing that makes projectile motion counterintuitive in so many ways, is because we can't see the x component, we can't see the y component. All we see is this resultant. Okay, trajectory means path. What does the trajectory of a horizontally launched ball look like? Well, it looks just like that. What does it mean to be a component? This is just what we call a part of something, one piece. Mathematically, we break these into trig functions, generally speaking. If you have Vx and Vy, and here is V, Vx is the x component of V, Vy is the y component of V. And so when we talk about the angle at which something is launched, then you would get the x component is the resultant times cosine of that angle, and the y component is the velocity, the resultant times sine of the angle. And you might recall this happening when we did components of forces. It wasn't very different. This here is a typical table of variables for a projectile problem. How do you find them? Well, the initial velocity is usually given, and the initial angle of launching theta. So these two are usually given, not always. But again, to find the x component, you would do V initial cosine of the angle. This would be V initial times sine of the angle. Now, what we're doing this year is we're only doing horizontal launches, so theta is going to be 0 degrees for a horizontal launch. If it was a vertical launch like we did in free fall, it would be 90 degrees. Acceleration on the x is always 0, right? We said y up here. Acceleration on the y is always negative g, right? Negative 9.8, which is what we use for free fall. The change in position has a special name on the x. It's called the range. And we find that using kinematics. Generally, we'll use dx equals voxt plus 1/2 axt squared. These are the, I'm going to tell you what to use 90% of the time or 95% of the time. This doesn't have a special name, right? This is generally your height. It's generally negative height. And you find it the same way. You're going to find it using delta dy equals boyt plus 1/2 ayt squared. Again, almost all the time. We'll cover this in the problem solving video that you'll do another day. Later velocity doesn't have any special name, but because we know that the x component, you have no acceleration, then the v final on the x has to equal the v initial on the x. So whatever you got in that first here has to be the same here. On the y, the final velocity, you have to calculate using kinematics. It's your initial y component plus ay times t, plus this times time. How do you find time? Well, that's, we're going to use kinematics. This is generally how we're going to solve for time. Usually using this. Okay, so that's how that comes into play.